let me introduce you to Isabel Rabey. She was born in Norwich in the UK. In 2013, she completed her master's degree at the Imperial College London, where she also did her PhD in the Center of Cold Matter, under the supervision of Professor Ed Hinz and Professor Mike Tarbert. In 2018, she moved to the Max-Planck-Institut of Quantum Optics for her first postdoc position. Here she works on the Cryo Fuge experiment in the Quantum Dynamics Division, which is led by Professor Gerhard Rempe. You might have seen Isabel in our teaser film for the lab tours. She and her colleague Florian Young were testing some sensors. By the way, this is the only lab that has no laser, at least not yet. But what they do with the Cryo Fuge is so stunning that we really wanted to share it with you. Because as things get colder, they get more and more interesting. But getting these cold temperatures in the first place can be quite challenging. On Monday, you remember that, or maybe you were with us, there was the tour with Tony. We showed you the complicated equipment and the expertise you need to cool down and control atoms. But when you have molecules, things are even more complicated. These particles have a much higher degree of freedom, which makes them very interesting to study, but also much trickier to control. Here at the MPQ, Isabel and her colleagues have developed the Cryo Fuge, a unique setup which allows them to cool, slow, and trap polyatomic molecules. And it's a setup that they have been working on for many, many years. So they were able, as I said, to trap polyatomic molecules, and this is something that only has been achieved here at the Max-Planck-Institut of Quantum Optics. Imagine. When the molecules are held in the trap, they can probe their interactions and for the first time study the collisional properties of molecules at low temperatures. So let's meet Isabel and her fascinating research.
So I work in the Quantum Dynamics Division with Gerhard Rempe, who is in charge of our group. And what is the main focus of our research in quantum dynamics is actually quantum networks. So having absolute control over single atoms in cavities as a node for a quantum network. And this is really one of the main focuses of our research group. But what I want to talk about today is something that's a little bit more in the future directions. So towards maybe one possible route that we can take for future quantum information, quantum simulation experiments, and that is molecules. So molecules are a bit more complicated than atoms because there are many atoms combined into one single particle. So for example, if we look at this picture here, this is an atom. We can just think of it as a ball, but a molecule has many of these balls all combined together. And what makes these molecules interesting is that they have a permanent electric dipole moment. So because they have some axis along which you can define your molecule, this means that it has a kind of orientation which gives it a dipole moment. And so what this means is that if you take two molecules and you orient them together, they have an arrow kind of already pointing upwards and they have a very strong interaction. So you could think of it, for example, as like a pair of bar magnets. If I take two bar magnets and they have this kind of force, and you try and put them together, they have this strong interaction. It's exactly the same, but it's an electric rather than magnetic effect. And actually this electric effect is more than 1,000 times stronger than the magnetic effect. And so what this means is that we can simulate things like magnetic, quantum magnetism, things like this. This interaction is very, very strong. So if we can get these molecules into a situation where they're cold and controlled in the same way as atoms, so we have absolute control over their temperature, their energy, their internal state, we can harness this power of this electric dipole moment and also all of their internal states to hopefully progress to a future situation where we have new quantum technologies, quantum things like this. But of course the problem is that because molecules are more complicated, they're also the very thing that makes them interesting, it also makes them very difficult to kind of harness and control them in this way. So getting them cold, getting them trapped, holding them in things like optical dipole traps that you saw, holding them in lattices that maybe you saw on Monday in the lab tour. It's just, we're getting there now, but it's very, very difficult. And one of the reasons is that a molecule, it can vibrate and it can rotate. So these make it interesting, it makes them sensitive to certain things, but it makes them very difficult to control. And so just as an example here I've drawn, so here's the atom that we saw earlier, and inside it has these quantized energy levels with a fixed spacing between them. And if I shine in some laser light with a photon with a fixed energy, what it can do is the population inside the atom can oscillate backwards and forwards many, many times, and many photons can be scattered. And this gives you this thing called laser cooling, and it allows atoms like this that are very warm to be cooled with the power of laser light, just through scattering photons many, many times. But the problem with molecules is that because they have this rotation and vibration, you end up with many more levels. And so if I shine in a laser here, often my molecule will get lost to one of these higher states and I can't scatter many photons. And so this makes it really, really difficult to perform things like laser cooling on a molecule. There are groups that do it, but it's only very special types of molecules. And so what we do in our group is we use the power of this electric dipole moment to manipulate the molecules to be slow, cold, and trapped, and then to perform experiments on them. So that's really the technique that we use in our group. Yes, and so maybe I can show you now how we actually do this. So we start off with molecules, and the molecules we use, they're just in a gas bottle. So here you can see, maybe if I come around here, you can see two types of molecules we have in the gas bottles, and they're just at room temperature, so 300 Kelvin. And all we do is we feed them into the vacuum chamber, and maybe we can swap around. And the first step we want to do is to cool them down. And so this is where something called our buffer gas cell comes in. So we can have a look. Okay. Do you need the torch? Is this good?
That's nice.
Yeah, okay, great. So this is the buffer gas cell. So what we see here, all of these things here will be cooled down to 4 Kelvin. So room temperature is 300 Kelvin, but in the end, when everything is closed up and this is under vacuum, all of this part will be cooled down to 4 Kelvin. So this means minus 293 degrees Celsius, so very, very cold. And what we have here, so maybe if I point, so the molecules come in down this line here and into the back of this cell. So this is what we call the buffer gas cell. This is just a box essentially, and this box is cooled down to 4 Kelvin. And so this is the cell, and I'm also saying the word buffer gas, and so what this means is it's a neutral, non-reactive atom, something like helium or nitrogen. We flow it into the cell, and I think you can see it here. So this line here is going in, and this is just the buffer gas. So this is cooled to 4 Kelvin. So molecules that come in at 300 Kelvin are being cooled slowly as they enter in the line. But much of the cooling actually occurs inside the cell, where they bounce around inside here many times, colliding with the helium, neutral helium. No reactions are occurring, but they're just transferring the energy until eventually enough collisions occur that they exit the cell and are cooled to 4 Kelvin. Okay, so they basically from the top here, they start at 300 Kelvin, and by the time they exit at the entrance of the cell here, they're at 4 Kelvin. That's the plan anyway. So this is the cooling part, and it's the cryogenic part, or the cryo part of the Cryo Fuge experiment. Okay, and so this is all just totally generic. So if I want to study a different molecule, I can just change the gas bottle, and a different molecule at 4 Kelvin comes out at the end, which is really, really nice. And so the next part is we have to then get the molecules that are cold towards the experiment to perform measurements and see what's going on with them, perform more experiments. And so what we have here is an electric guide. So maybe if I shine the torch. So this guide is made up of 4 rods, and the spacing between the rods is 1 millimeter or less. So at the very center, it's 1 millimeter. If the molecules are traveling down the very center, then it's 1 millimeter. And these are held very precisely. So I have to also say that our workshop here designed and made almost every component you can see here, and it's really incredible to work at MPQ and have such great technicians. So these rods are held in place extremely precisely, and these rods here are also charged up to very high voltages, so they can go up to about 10 kilovolts. So what this means is that I have one of these rods charged to 10 kilovolts and the other rod next to it charged to negative 10 kilovolts. So there's a potential difference of 20 kilovolts across the spacing of around a millimeter. So it's really incredible fields, and this creates a guiding potential for the molecules. So if we just go to the poster, this is how the rods would look like. So we can guide molecules at the center here if we charge the rods in this configuration. So you can see here, this one would be plus 10 kilovolts, minus 10 kilovolts, minus and plus. And this creates a guiding potential for the molecules, and we can just move them around the lab with this by bending it and having straight pieces and so on. And that's all the cooling part and moving the molecules around the experiment. So then the thing is that although they're still very cold, these molecules, so there are many more, so they're kind of, they're just cold, but they're still traveling quite quickly. So normally they come out of the buffer gas cell between kind of 50 up to about 200 meters per second. And this is way too fast for us to trap or do anything with. And so this is where we need something called a decelerator to slow them down so that we can then hold them and perform studies on them. So this is something that's very special to MPQ. And this was entirely designed by our group. So it's called a Centrifuge Decelerator. So the way it works is, this is a plate of so there are 4 of these plates inside. And how best to explain? So basically there's a guide. So the guide that I just showed you inside here, it's guided all the way around the outside here in a spiral. And what happens is the molecules will enter into here, and the centrifuge is turning at the same time. So it's spinning around like this. And as they travel through the centrifuge, they're experiencing a centrifugal potential. So the way you can think of this is like when I have a bucket of water and I spin it around, this centrifugal potential is the thing that's keeping the water in the bucket. And it's this same force that is causing the molecules to slow down. So it's like it's climbing a hill because of this centrifugal force caused by the turning of this guide. And this is a one-of-a-kind, totally unique decelerator. It's extremely special, and so maybe if I talk you through the design. So here, all of these holes you see, this is for balance, because what happens is this centrifuge is turning, and it's turning at about 30 hertz, which doesn't sound like a lot, but actually it's rotating 2,000 times per minute. Okay, and this is all under vacuum, so 10 to the minus 6, 7, 8 millibar, and also it can be charged up to 10 kilovolts. And so as it's rotating, these holes stop it from doing any motion like this that could cause it to damage or break off and so on. So as it's rotating, these holes are keeping everything nice and stable and stopping this kind of backwards and forwards motion. And then here you have some little dimples as well, and this keeps, again, very precise separation. So what we would have in here is some ceramic balls, and this would keep, there's 4 of these plates held together, and these 4 plates would be separated by some ceramic balls. Okay, and so this plate here, this is this whole part inside here. So we have coming from the cryogenic buffer gas cell, we have this, they travel down here, you can see inside. Here you can see the guide again, so this is just a straight piece of guide. Again, held very, very precisely to be the same separation all the way through the experiment. And then they reach the centrifuge decelerator. So this is the motor. This motor here allows it to turn around. And of course, and there's also these red cables here provide the voltage to provide the guiding for the molecules. And so this motor rotates everything at around 30 hertz. And then they come out on the axis here. So they come out So they're traveling around the outside and then they spiral into the center and they come out down here towards our experiment area. And maybe I can just show you the full thing. So here's a photo of the fully assembled machine. So you can see, so this is where they would come in, they travel around the outside, and then there's an end bend here which allows them to come out on the axis of the thing. So this is the fully assembled situation. Yeah. Okay, good. So with this, we have managed to slow and cool molecules, and it's one of the, I don't want to make big claims, but it's one of the brightest sources of molecules. So what does this mean? So it's got a flux of, extremely high flux of molecules, so below 1 Kelvin, and it's one of the best sources of cold and slow molecules in the world. So I don't know, for the experts out there, if you're watching, it's more than 10 to the 10 molecules per second below 1 Kelvin, and these molecules are actually confined inside a guide. So they're confined within this 1 millimeter radius of guide when they come out. So this together is what we call the Cryo Fuse. So it's a combination of cryogenic buffer gas cooling and centrifuge deceleration. And it's a totally amazing, but also extremely unique source of cold molecules. Okay, so when I arrived here at MPQ, this was all set up and working very nicely, and the next step was to then take these cold molecules and do something interesting with them. And so what we have installed here is, so if we have, of course, these molecules, and actually maybe I should say that when they come out of the centrifuge, they're at about 20 meters per second or slower. So this is in a kind of trappable regime for us. And it allows us to hold on to these molecules. So here they come out around 100 up to 200 meters per second, and when they come out of the centrifuge decelerator, they're at about 20 meters per second. Okay, and so then, yeah, this is the centrifuge. So here they're cold, so they're about 4 Kelvin, and they're about 20 meters per second. Or well, the ones we can trap are at 20 meters per second, but there are some that are higher, but we can't trap those. So we're kind of interested in the ones that are 20 meters per second. Good. So there's still some that are very fast. So there's still some kind of up to about 80 meters per second, but the cooling really allows us to get as many as we can into this trappable regime. And so here we have a little bit more because there's still some fast molecules left. So we have this S piece, which allows us to filter out some of the fastest molecules. So the molecules that are really traveling still at speeds which we can't trap, we want to get rid of them. So if they're faster than the potential of this bend, they just exit through the guide.
Where's the guide?
It's this S piece you can see inside. So this is part of the guide, but it's just been bent into an S shape to allow us to filter out these fastest ones. Good. And then we get to the trap. So this is where now we want to perform some experiments on them, see what's going on. And a big part of performing experiments is being able to hold on to the molecules, perform studies on them for a long time, rather than just having them flying through here for a few milliseconds. We want to have several seconds of interaction time, studying them, and so on. And so this is where we get to the trap. So I don't know if you can see, so maybe you want to go in. So this trap is also unique and extremely special to only MPQ. So it was designed by our group leader, and what it's called is a microstructured electric trap. Okay, I can go from the top. So it works by basically trying to create a large 3D potential of electric field. And the way it does this is by, so this is an old broken plate. So can you see? So maybe you can see the microstructured part of it on the surface. I don't know if this is better. So the way it works is that there are the microstructured part is an interleaved electrode, so it looks like this, and each of these are charged to positive and negative, and you end up with a repelling field. So if we look at the poster, So this is a kind of schematic of the trap. And so this is this microstructure I was talking about. So each of them are charged plus minus, and you end up with a field that looks like this. So this is the low field. So in the same way here where you had a low field for guiding the molecules, here in this case we have a low field, but it's in 3 dimensions like a box. So we can load in the molecules and store them in this trap box, which has a box-like potential, and we can hold them in there for several seconds and perform studies on them. Okay, so this is in no way, so we're still at temperatures of around 1 Kelvin, and so this is really, it's still extremely warm compared to some of the experiments that you've seen in the week. So yeah, I want to just stress that we can do interesting stuff even though the molecules are still at 1 Kelvin. And the route that we're going down is kind of the direction of cold chemistry and collision studies. So even though maybe our overall goal is quantum simulation or quantum information with molecules, there's still a lot of interesting physics on the way to try and find out and see what's going on. Because with molecules, no one really knows what happens actually when it's 1 Kelvin. No one really knows what happens when 2 molecules come together. Do they stick together? How do these dipoles orient themselves? And all these things we want to try and find out and study them, and this is the thing that we're trying to study. So yeah, so how much time do we have?
We still have about 30 more minutes.
Okay, fine. So maybe I talk to you a little bit about this collision idea. Maybe I should just say how we detect the molecules. So this last part here, this is how we detect the molecules. So this is a quadrupole mass spectrometer. So the reason why we use this is because, again, it's completely general. So everything I've told you so far allows us to just simply change the gas bottle at the end here, and we can change the molecule and study a different molecule. Okay, so we don't have a special detection scheme for one specific molecule. The mass spectrometer here allows us to really detect any generic molecule that we choose to study and put it into the trap. So as long as it's not too heavy and as long as it has this dipole moment, we can put it into the Cryo Fuge and trap it and hold it and study it. So that's a very nice part of this experiment.
There is a question that actually fits quite well at the moment. How do you probe what the molecules are doing without a laser? Let me plug you back in.
It is challenging to probe things without a laser. So what we have to do is we have to be very smart, I guess, with the way we detect them. So we can do things like turning voltages on and off. We can shine in, for example, radio frequency or microwave frequency radiation, and that allows us actually to address a lot of the molecules. So if you remember, I said that there's rotational states and vibrational states. We can address those with microwaves and radio frequency, and there's also extra smaller levels inside which we can also address. And so by playing tricks with the electric field distribution in the trap, by shining in things like radio frequency, microwave frequency, we can manipulate the states and also turn voltages on and off, and it allows us to study in a generic way molecules. But yes, having a laser would be nice, and yeah, but it's not that we can't do things without a laser. So yeah, so because of this generality, we really like to try and keep that, so we have to make some trade-offs in terms of that. Good. Okay, so if we want to study collisions, this is one of our goals, kind of a cold chemistry effect. So this is what I've drawn here. So I've got a box of molecules, like our trap, and there are 2 types of collisions that occur in our trap. So there's the elastic kind, which we think of them as kind of the good collisions. So elastic ones are really like a kind of snooker or billiard ball collision. So 2 hard balls just colliding together and energy is being exchanged between them. So these are called elastic collisions. There's another type called inelastic, and these are they're often thought of as the bad collisions. So what this would mean, for example, is that an inelastic collision would cause one of the molecules to be lost from the trap. So it's really a collision process which causes us loss. And the reason why elastic collisions are good and inelastic collisions are bad, okay, inelastic collisions are still interesting to study because we don't know how they behave. So if I take a molecule in an electric field, how does that inelastic collision process occur? What's going on? It's still interesting to study, but we're atomic physicists and we want routes to colder temperatures and more control and so on. And so elastic collisions are the good ones that we want to see. And so the reason why elastic collisions are good is because of something called evaporative cooling. And we can think of this, so if this is my energy distribution of molecules in the trap, so it has some probability of being at a certain energy. And what elastic collisions do is simply exchange energy. So if I have a molecule at this energy here and a molecule at this energy, then all that happens is maybe if an elastic collision occurs, this one might move here and this one might move here. And so it's just exchanging energy. But what we can do is kind of take control of this and try and use this to our advantage for some future studies. So for example, so what would happen in an elastic cooling process is we would cut away the hottest molecules here, and we would do this by this radio frequency that I was talking about earlier. So we manipulate the distribution of the electric field and some radio frequency light, and we can cut away this hottest part of the molecules. And in this case, and so you end up with a distribution that looks a little bit funky. But what happens is that after some time, we allow these good collision processes to occur, and you end up with a distribution that's colder than it was before. And so what this means is that by cutting away the hottest molecules, I end up being colder. And it's just, you can think of it like evaporation. So if I have a puddle on the floor, even though it's not boiling or anything like this, eventually the water disappears, and this is evaporation. And so it's the same idea. The hottest water molecules, if I've got a puddle, the hottest water molecules are evaporating away and the puddle gets energetically colder. You could think of it like this, and it's the kind of same idea. If I cut away the hottest molecules and I have these elastic collisions occurring, this whole sample as a whole gets colder. And if I keep doing this and keep doing this and keep doing this, eventually it gets colder and colder and colder. And this was actually a crucial component for making Bose-Einstein condensates. I don't know if people know about this, but it was a big step towards making and achieving a Bose-Einstein condensate. It's having enough good collisions occurring compared to the inelastic, compared to the bad collisions. And so it's these things that we're trying to study at the moment. So inelastic collision processes are interesting in themselves because they're kind of the chemistry and kind of the kind of meat of the chemistry, but then the elastic collisions are what we really want in the end. And we want to try and study this and see if it's even possible to get to a Bose-Einstein condensate of molecules, for example, if these properties allow it to happen. Good, so that's the one side of it. And okay, it's the 60th anniversary of the laser, so I should talk about, there's no laser, you haven't seen a laser yet, and our actual next step, like maybe a longer term goal of our experiment, is to get even colder. And so we do want to incorporate a laser into our setup. And do you remember I said before that we can't use this kind of scattering technique that atoms use? So in this case here, I'm scattering many photons, and each photon is taking away a little bit of energy. But we can't do that with our molecules because in some cases they just break apart if we excite them, or something horrible happens. So what we have to do is we have to come up with a different technique. And this technique was developed by our group. And we're the only group in the world that actually use this cooling technique because we use such different molecules and such special molecules. And so the way this works is it's called optoelectric Sisyphus cooling. So it's the opto part is the laser and the electric part is the trap. So we have to use the distribution of the trap, so the electric field, to help us get colder. And what I've drawn here is a schematic. Let's see how it goes. So basically we have some energy levels inside the trap here, and I have two quantized energy levels. So in this case, if you remember in the atom, I just had two levels, but the molecule, it has many more levels, and we can try and take use of this and use these levels to our advantage. And so what I have is I have two of these many more levels, and one of them shifts a little bit in the electric field, and one of them shifts slightly less. And this is it. And then what we do is we create a loop with which we can extract energy. So we use a laser to excite up, it decays back down, and the energy we extract, rather than having a photon scattered, so each scattered photon is removing energy, that's not what is happening here. What's happening is the energy that's extracted is proportional to the shift in the electric state. So we're cooling, but it's subtly different to laser cooling. So that's kind of a bit more technical, but this is our plan. So in the future, we want, maybe we can measure these elastic collisions, but of course everything gets more interesting the colder we are. So the more quantum it is, the colder we are. And you can imagine a situation where we're at 1 Kelvin now. Let's say we can get to a millikelvin or a microkelvin or a nanokelvin. Everything starts to become more and more interesting. And for example, if you want to study collisions or extend upon our collision work that we've been thinking about, you could imagine a situation where we're so cold that we have a single quantum state that is well defined and another single quantum state, and they interact, and you can probe the internal states, maybe probe what's happening during the collision. This is really like a dream for collision studies, to have really ultimate control, and this can only really happen as you get colder. And so this is really a longer term goal of our experiment, and another experiment in our group is working on this, getting colder and colder and colder and studying this. And of course, then once you're colder, once you have more control over the molecules, you can start doing many more interesting things. So it's really all about progressing the field of cold and ultra cold molecules to a point where we can start to study this. And of course, there are many more experiments. This is not the only molecule experiment out there, but on trying to progress the field to this level that atomic physics is in, where you really have absolute control over single atoms, and we would like that over molecules, but of course also finding out interesting physics on the way. So it's we're finding out interesting stuff, but also looking to get colder.
I have a couple of questions.
Yeah.
So the first one is, what is the hardest part of your work?
The buffer gas cell is the hardest part. Yes, we'll show you again. This is the hardest part because it looks so simple, okay? So it's a box of copper and it's very, very mechanical, right? So you would think that it should just work. And most of the time it does, but quite often it doesn't. I don't want to say often, no, that's not true. The PhD students have been working incredibly hard getting everything to work nicely, but of course this is the most kind of dark arts part of our experiments. So the problem is that, for example, if I shine in microwave frequency into the trap, it's very well defined. I really know what's going on there. There's only so many things that can go wrong, whereas here, it seems to be a bit black magic sometimes. And this makes it very annoying for physicists because we just, you know, according to us, everything is assembled the same and fixed together the same, but it's different, and that's really annoying. So this is one of the things that we've spent a lot of time on improving, trying to make it colder, because the colder we are, the more molecules we can trap at the end. And this is really one of the things that we've been trying super hard to get very nice. And if it's not working, then it's very annoying. And also I should mention that, so it's open at the moment, as you can see, so it's cooled down, it's at 300 Kelvin. But if we want to, let's say we want to change something on it, we open it, we change something, we have to cool down to 4 Kelvin. This takes about 4 or 5 hours. And we test it, see if this change has helped us. If it hasn't and we have to change it back, or for whatever reason we have to warm it up, this takes another 6, 7, 8 hours. depending on what's going on, and so every change is very slow, and this can be quite annoying. It's not so if we tweak it and change something, we see an immediate effect. We have to really wait a kind of day cycle to see if we've made any difference. So that's that's the hardest part. It's very annoying.
It's a question from my side, because in the video, in the teaser video, we talked about the sensors.
Okay.
What are the sensors for? Those are the sensors, right?
Yeah,
Up
so
here?
all the wires you see that are sensors, and also for heaters. So I wonder if you can see, so for here, for example, is a sensor. So this sensor is measuring the temperature of the buffer gas line, because one problem we had recently was that the buffer gas line broke and we had to replace it, and this buffer gas was not getting cold to the same temperature as the cell. There's a sensor here. This is on the molecule line. So the molecule line we keep heated actually to 140 Kelvin. So this is another technical challenge. So this cell is at 4 Kelvin and the molecule line is at 140 Kelvin. So 136 Kelvin difference. And I don't know if you can see in the back here, but the only isolating thing we have is this, it's called Vespel material. It's like a ceramic material. And so the reason why we keep this so warm is because if the molecules enter into this molecule line, they actually freeze. And so we don't get any molecules coming in. So because the flux of molecules is so high coming into the cell, they freeze inside. So they're not they freeze inside the line, and then we get no molecules out. And so this temperature has to be monitored to keep the molecules from freezing inside this line. And then we also have to monitor the temperature of the cell to see if anything's going wrong, so it should be cold. So that's the main sensors, and then so we also have a heater here, and a heater, this is also a heater to basically allow us to warm up to room temperature quicker so we can change stuff. So this heater allows us to do that. Yes. And I mean, also we can talk about, so this buffer gas line, so it's this copper thing here that goes all the way around. So we have to really make sure that this is cold to 4 Kelvin, and so we have it cooled on this stage, and this up here, this stage is 30 Kelvin, so this is like a pre-cooling thing. So this is really, we have to make sure that there's a long line of copper piping here to make sure that our buffer gas is really at the same temperature of the cell, and that we're not adding unnecessarily a lot of heat. Yes.
Thank you. Another question that was asked, what would happen if you turned on the centrifuge at atmospheric pressure?
Good question. I'm not actually entirely sure about that. So this was actually designed and built before my time, and I've never wanted to rotate it in atmosphere. So I don't know the answer to that question, I'm afraid.
There was oh, there is more question.
Yeah.
How cold can you realistically get at present?
Okay, so the temperature of our molecules is, when they come out of here, is 4 Kelvin, and also here 4 Kelvin, but we can only trap 1 Kelvin temperatures. So any molecule that has an energy of more than 1 Kelvin, we can't hold it in the trap. So that's really our upper limit. That's like the trap depth, we would call it. But another molecule experiment in our group, they work actually on cooling molecules, so using this technique I showed you with the electric field, and they can cool the molecules down to 400 microkelvin. So that's 10 to the minus 6 of a Kelvin. So we're at 1, and they're at 400 microkelvin, so that's 0.0004, something like this, of a Kelvin. So that's kind of the status of our group. There are other groups out there who have achieved molecule temperatures of kind of 5 microkelvin, so even a factor of 100 or so lower temperatures, but that's really like the state of the art of molecules at the moment. And so, yeah, of course, the colder we can get, the better. Yeah.
Here's a nice question. What about your job and research do you love the most?
The challenges. So every day is very challenging and I have to think about it and use my brain, and problem solving is something I really enjoy. So taking all these different pieces of physics and also a little bit of engineering, for example, from the buffer gas cell, and applying them in a way to solve these problems. And the problems can be so annoying, like one of these cables is broken, but having the kind of capacity to figure it out, I mean, that problem is annoying. That's not a fun problem to solve. But like thinking about, especially for example, thinking about the collisions, thinking of models and studying and trying to use all this physics but also engineering knowledge and coming up with this idea, yeah.
So, there is an earlier question. What if we cool up to okay temperature, will the molecule stop moving?
Yeah, so the temperature is related to energy. And so when I talk about temperature and energy, they're very interchangeable in atomic physics experiments and molecule physics experiments. So the colder I get, the slower the molecule gets. So for example, here they're traveling 200 meters per second, but the colder they get, the slower they are. And so that's really, yeah, they're very interchangeable, these two things. And so eventually you get colder and colder and slower and slower and slower, and yeah, they're very interchangeable terms. Yeah.
And here's another question from the start. What's the application of your work? And you've been talking about the Bose-Einstein condensate with molecules as well. What, maybe that goes together, I don't know, but what would be the great thing about it? Why would that be so important? And what other practical applications do you have for that?
So the Bose-Einstein condensate of molecules, for example, would be, they're very interesting. So a Bose-Einstein condensate of atoms, do you remember I said it's just like a kind of ball? And they condense down, and of course it's very interesting to study, but the difference with molecules is that they have these dipole moments. And so you get very interesting things happening between molecules when they're extremely cold. And there are certain experiments that do this with atoms. So there are some atoms that have a magnetic dipole moment, and they are studying these dipolar Bose-Einstein condensates. And there's very interesting things happening in this field, and it's a very, very active field. And the electric dipole moment is even stronger than the magnetic dipole moment. So there's very interesting things to study. Okay, so that's the one side. Technological applications. There are so many proposals coming out all the time. And I mean, really any proposal, many of them make use of this dipole moment. So for example, I could put all my molecules into a lattice, like we saw in Tony's experiment on Monday. So a lattice of molecules, and they have interactions between each other. And for example, if I flip one, others around it will feel it. So you could imagine a situation where I tune the dipoles and they're all interacting, and it's somehow like a quantum simulator. You could think of them as a quantum information processor where I have dipoles in a line, and I can somehow address each of these molecules individually, and if one flips, then the information is transferred. It's the same ideas over and over again. You could, I mean, another thing that's very close to my heart, which is what I did my PhD in, is molecules, because they have this vibration and rotation, and they have very different structures, they're also sensitive to fundamental constants in a different way than atoms. So what I did my PhD in is the electron's electric dipole moment, but things like the proton to electron mass ratio, the fine structure constant, all of these things can be measured by molecules extremely precisely in a way that atoms can't. And of course, with every precision measurement, the more interaction time you have, the colder you are, the better your measurement can be. So it's really, a lot of these techniques are about improving these precision measurements. Of course, quantum information, quantum simulation is a big driver, and all these interesting physics along the way. Yeah.
So we're talking about interest, and there is the question, what made you want to be a physicist?
Do you know what? I think it was my teachers at school. So I had this female physics teacher, actually, which I think is quite unusual. And she was very good. And also I had two physics teachers, and they really encouraged me to apply. And at first to physics at university. And also, I mean, a lot of the careers when you're a scientist, they want you to be doctors, and I just hated biology, so I didn't want to be a doctor, a medical doctor. And then at university, I just really, I worked in a lab during a summer internship in an atomic physics group, and I just loved it. And I loved the group, first of all, and I found the atom part very interesting, and so that really motivated me to do a PhD. That experience of doing summer internships and also doing some lab course, those two things. And I think, doing my PhD, I loved it, and that's it.
So you could say it started off with a good role model in the end.
I think so, yeah.
So we are coming to an end. There is about 9 more minutes. If there is more questions, feel free to ask your questions. Otherwise, I would ask you, Isabel, is there anything else that we would like to tell the audience, maybe why they should be more interested in physics?
What we're doing is very kind of like a little bit on the side of Gerhard's research. And there is some absolutely amazing experiments in our group where they have incredible control over atoms. And you should go and look that up, because their experiments are also amazing. And we can only showcase one, but I think there's so much interesting stuff going on here.
Will you pursue a scientific career after your time here?
I don't know. It's extremely competitive and challenging. And the thing I love about being a postdoc is the hands-on experience of working in a lab. And I think it changes as you become more and more senior. You become more and more of a manager and less of a really hands-on. So I need to decide soon.
How much longer will you be here? And then I ask you the next question as well, which is very unique and goes in a very different direction. What do you think of the many world theory?
I would say I lean on the side of negative, but I don't spend much time thinking about the many world theory. And yes, I'll be at MPQ 1 more year until the end and start of next year.
Thank you, Isabel. You did a great, fantastic job. And I have good news. This is working so well that actually our managing director wants us to keep on going with this, so it's gonna be a regular thing, and we're gonna see some more labs of the quantum dynamic division in the future. There is no start date yet. Right now we are doing our series of lab tours for now. Tomorrow we will be meeting Fabian Schmid, who works for the laser spectroscopy, which is actually the division of our Nobel Prize winner, who won his Nobel Prize for the frequency comb, which is a very unique technology, and you might learn some about that tomorrow as well. So thank you all for joining us. I hope you join us again tomorrow at 5 p.m. And let's say goodbye to Izzy.
Bye.
Bye, guys.